All right, so for our next section of the day, we're going to have Vassilios Mewes. He's going to be talking to us, continuing on the theme of neutrino radiation and hydrodynamics in GR. So take it away.
All right, here. Is that close enough? All right. First of all, thanks to the organizers for inviting me here. It's always nice to come back to see the familiar faces of the Einstein Toolkit and to go back to my origins as a relativistic astrophysicist. So today I'm going to talk about neutrino radiation hydrodynamics.
Vassilios, your sound is very low. Are you using a microphone?
I am. Is that better? The mic on?
It'll do. Thank you.
All right, I'll try to shout. So I'm going to talk about neutrino radiation hydrodynamics with Flash-X and Tornado. There's not going to be MHD, there's not going to be GR, but there's going to be spectral neutrino transport for supernova. So bear with me. All right, here's the outline of my talk. I'm going to introduce some background. Why do we care about neutrinos? Different methods. We've seen many excellent talks today already about the topic. So thanks to them, I don't have to go into too much details. I'm going to briefly introduce the ExaStar project, which is a large collaboration within the ECP, where we basically built these codes that I'm going to present. I'm going to briefly talk about Flash-X and the physics modules that we use for core collapse supernova simulations. I'm going to show some results from 1 and 2D simulations, some outlook, what we're currently working on, what's still missing. And then I'm going to introduce the OLCF briefly and the computing resources that we have available and kind of try to attract new users away from TAC, I guess. All right. So the main question in core collapse supernova, so it's basically the death of massive stars, a bit larger than 8 solar masses. The star begins to collapse when the iron core, basically after an extensive amount of fusion, has reached iron. So iron is a stable isotope because it's at the peak of binding energy when you basically cannot generate energy anymore by fusion and by fission also. And once it reaches the Chandrasekhar mass, the core is basically not, the degeneracy pressure is not large enough anymore to protect you against gravitational collapse. So it will basically start collapsing onto its own. And during the collapse, the core will reach supernuclear densities. And at some point around 10 to the 12 grams per cubic centimeter, neutrinos start becoming trapped. And then you really need to care about the transport of neutrinos in the collapsing star. The equation of state basically stiffens, and there's a bounce shock that forms at the surface of the newly born protoneutron star. But eventually the shock stalls because it loses energy to the dissociation of nuclei and losses to neutrinos. And while all this is happening in the core, the outer regions of the star that are still infalling are causally disconnected. So you basically have the entirety of the star falling onto the shock. And there's a really delicate pressure balance between the ramp pressure of the onfalling material and what is happening below the shock. And then the protoneutron star is radiating neutrinos copiously, which are interacting in the region between the protoneutron star and the shock radius. They're interacting with the material. And the neutrino heating mechanism that is proposed to revive the explosion and actually drive out the shock and so that we can see the explosion is basically concerned with how do you connect those neutrinos that carry the energy from the protoneutron star and to connect to tap into the liberated gravitational binding energy of the core in order to explode the outer layers of the star. And in multi-dimensions, there's multi-dimensional instability. So there's buoyant bubbles forming. The shock was actually shown to be non-stable to perturbation. So it starts wobbling around in the standing accretion shock instability. And all of these together kind of form the puzzle that has that is responsible for driving the shock and the explosion. And the physics needed to model core collapse supernova is basically all 4 fundamental forces of nature. So you have gravity, you have to evolve the fluid as it collapses, and basically we have in Flash-X we have a finite volume hydrodynamic solver that I'm going to briefly introduce, and a multipolar gravity solver. As I said, there's no GR yet, but we're working on this. And then basically, you need to solve the Boltzmann equation for the neutrino transport. And I'm going to go into details of how we do that. In Thornado, we use a discontinuous Galerkin spectral two-moment radiation transport. And then finally, the neutrinos, there's phase space advection, and they interact with the fluid through the weak interactions. So our code WeakLib has support for tabulated equations of state and those neutrino weak interaction kernels that we can interpolate onto the grid when we need them in order to evolve the neutrinos in the fluid in a coupled matter. Of course, we also need an equation of state. And I'm going to show you how, later I'm going to show you how we use the NSE equation of state at high densities where everything is in nuclear statistical equilibrium. And outside of it, when the temperature or the density becomes too low, you cannot assume this equilibrium anymore. And then you basically actually have to evolve the composition of the material, taking into account nuclear reaction networks. And we have a hybrid method that combines those two regimes. And then recently we started adding muons. So we've heard talk about the electron fraction. And usually the baryonic equation of state is always tabulated in terms of the proton fraction, because if you assume that there are no muons in the system, the electron fraction and the proton fraction are equal. But once you take muons into account, you actually, this degeneracy breaks, and you have to really have two new lepton species and fractions that you need to evolve. And then, so as the fluid and the neutrinos self-consistently interact, there's basically lepton and form momentum exchange between the fluid of neutrinos, and that is being governed by the continuity equation. And the conservation of the matter stress energy tensor is now directly coupled to the evolution of the neutrinos through the collisions or through the weak interactions that the neutrinos have. So you need to sum the contributions from all the 6 species as they evolve and as they exchange momentum and lepton number with the fluid. And if you just care about electrons first, you basically need to evolve the electron number density. And if you later start doing muons as well, you need to evolve the muon number density as well. And together, the stress energy tensors and the momentum have to be individually conserved when you take into account the neutrinos and the matter. So similar to what we've always seen in GR, where the space-time tells matter how to move and the matter tells space-time how it is curved, we have a similar situation here where we have 2 different agents of nature that have to be self-consistently evolved together. And then we've seen similar presentations in the neutrino talk so far. There's different ways of actually solving that problem. So we have different methods, such as full Boltzmann solvers that Maitreya introduced in his talk. And then basically the advantage is you have full accuracy, you handle the optically thin and thick regimes correctly, but it is extremely expensive because you have 3 spatial and 3 momentum dimensions where you need to discretize your equations, and things become really expensive. And in 3D, it's just not feasible yet to do that. Then we have Monte Carlo transport, which is similar to how you do higher or multidimensional integrals with Monte Carlo much more efficiently than you do them with quadratures, just because of the cursor dimensionality. Jonah introduced in his really nice talk this morning Monte Carlo transport, which handles complex geometries well. It does really well in the free streaming regime, but it's also noisy because it's a statistical method, and it can become really expensive in the optically thick regime. Finally, there's moment schemes where you basically evolve you do a moment expansion of the full distribution function, and then you evolve the lower moments. So usually it's the M1 is the 0th and the first moment, so the number density and the number flux basically. And this is a tractable method, and it allows a natural coupling to the fluid evolution because you end up with equations that look really similar if you've done MHD before. The problem with that is that it needs a closure, so you need to connect the optically thin and optically thick limits together. And it's also, as we've seen, it doesn't handle crossing beams or multiple sources at angles in the free streaming regime really well. And finally, there's multi-group flux-limited diffusion, which is a very fast method, and it's really good in the optically thick limit, because in the optically thick limit, the neutrino transport is essentially diffusion. But you need to have flux limiters in the free streaming limit, otherwise you can end up with superluminal propagation speeds. Then finally, there's the guided moment formalism that Manuel introduced this morning, which effectively combines the best of both worlds from Monte Carlo and M1. But I think if I understand it, there's still a need for fine tuning for that matching function between Monte Carlo and the M1 regime. And he was talking about gray transport. But when you do spectral transport, as you can see here on the left, which shows the neutrino mean free path in kilometers for a typical post-bounce profile at 100 milliseconds post-bounce as a function of radius, you see that when you do the matching between Monte Carlo and M1, or the closure as well, if you do it in a spectral manner, it actually, you see that spectrally there's no, at a given radius or a given spatial point, the closure is different for different neutrino energies. So this, I think, will be an added complication to the guided moment formalism. So you can see that when we talk about the optically thin and the optically thick limit, it basically is concerned to the fact that the mean free path might be small compared to the relevant time scales of the spatial scales of the system, or it might be large. And in Thornado, we use an M1 scheme. So let's see how that will look like. So I said the equations look very similar to your GMHD equations. So we basically have the phase space advection of the conserved number density and the conserved momentum density. And then, I don't know if you can see my mouse or not. I don't think so. Up there, you basically have derivatives with respect to the energy, and you have some source terms that come from the collision, as I was talking before. And in this moment method, as I mentioned before, we basically need a closure to specify how the higher order moments that appear in the equations are related to the lower order moments. And the moments are defined, of the distribution function are defined in the following way. So it's basically taking the propagation vector and then doing dot products and integrating over the full distribution function. In the results I'm going to show you, we use the Minerva closure. The Minerva closure provides an analytic expression to close the system of the M1 evolution equations, and it's basically approximating the Eddington tensor based on the flux factor, which assumes a maximum entropy angular distribution for a given flux and density in a spectral sense. So we have an Eddington factor that is spectrally dependent. And it's basically providing a smooth transition from the optically thick to the free streaming regime. The flux factor is defined as the flux divided by the number density in each cell, and we're using units where the speed of light is equal to 1, so that's why the flux factor goes to 1 and not to the speed of light. And then here, that is the expression for the closure that we're using. And I want to point you to the fact that, unfortunately, or you would expect it, that's how nature works. So deep inside the protoneutron star, where the densities are really high and the transport is in the diffusion regime, on the optically thick regime, the flux factor is basically 0. And then as you go up, there's a sharp rise until it reaches 1 in the free streaming regime. And of course, the magic, or what you really care about, this whole shock revival mechanism, that is happening in that precise region where the flux factor goes from the optically thick to the optically thin regime. So it is really important to get the flux factor correct in that regime. All right, so after a bit of intro, let's jump into exastar, which was a team effort in order to build a component-based multiphysics AMR toolkit for computational relativistic astrophysics. It was a program within the exascale computing project that has funded quite a few people for, I think it was 7 years in the end. And I joined towards the end of it at ORNL as a postdoc and then as staff. So the overarching, similar to, I guess you could, if you want to do equivalence to the ET, the overarching physics are coupled in Flash-X, which has their own mesh refinement driver, and we currently have support for either Paramesh or AMRX. So Paramesh is an octree-based AMR framework, and AMRX is patch-based. And we basically have GPU support, programming model via directives. So we have both OpenACC and OpenMP. And we keep both because different hardwares play nicer with one or the other. So if you use NVIDIA GPUs, you'd rather use OpenACC because through their acquisition of PGI, they have better support for OpenACC, and OpenMP plays nicer on AMD hardware. We have linear algebra libraries that are often dedicated and vendor provided. So in Thornado, we use QBLAS or HIPBLAS, and then also support for 1MKL and third-party products such as Magma. As part of the key physics module, so we have Thornado, which is spectral two-moment neutrino transport, which is fully offloaded with OpenACC and OpenMP, and those GPU linear algebra libraries. We have MHD, Newtonian MHD, and GMHD support via Spark. Self-gravity is currently being done in a Newtonian or G-effective potential multipole solver that is currently CPU only. We have nuclear burning. We have the XNet code. So that does the composition evolution where you cannot assume nuclear statistical equilibrium anymore. And that is the GPU port is being done with OpenMP offloading. And then finally, we have NSE equation of state and the neutrino opacity tables in WeakLib. And those are fully offloaded with OpenACC and OpenMP as well. The code is publicly available, but due to licensing requirements from Argonne National Lab, you basically they have to keep track who they've given access to the code to. So if you want to get access to the GitHub repo, you have to send an email to the maintainers.
You just have to email to the code repository management people for Flash-X, and then they just need to know your GitHub username and right. And I think it's actually part of DOE's restrictions to keep track of who's going to get the code. But I think that's your only restriction. The rest of your stuff is definitely open, public, and on like GitHub and so on.
Yes.
Yeah. Okay. Good. Yeah.
All right. So Spark, the code that we use for the Hydro evolution, is a standard high-resolution shock capturing finite volume code. We have a variety of reconstruction schemes such as Vino5, MP5. At some point, I've implemented a well-balanced TVD where you basically have to reconstruct the pressure, taking into account the gradients of the gravitational potential. We have a couple of Riemann solvers such as HLLC, HLLE. There's some, you can use HLLC and then switch to HLLE inside shocks, for instance. We have flux corrections at mesh refinement boundaries. So the code conserves matter even with mesh refinement boundaries. And currently, Spark uses RK2 or RK3 time integration. And we can do telescoping for reduced ghost zone exchanges, where it's basically, I think the name in the Einstein toolkit was tapered grids, where you basically add an additional layer of ghost zones to the outside, and then you basically start evolving from the outside in, and that's why you don't have to communicate during sub-steps and the time integration. Then finally, let's talk a bit about Thornado. Thornado is short for the toolkit for high-order neutrino radiation hydrodynamics. So the way neutrino transport is implemented is a bit of a mouthful. It's a realizability preserving discontinuous Galerkin IMAX method for the number conservative order V over C two-moment model, which is consistent with the Eulerian frame energy equation. You can read the glory details in that paper from 2025. Given that we have some applied mathematicians working on this, and the originator is an applied mathematician. It's very dense on the mathematics. But basically, they've proven that the evolution framework does what it's supposed to do. It's GPU offloaded, and Thornado operates on a single block. So there's no MPI parallelism within Thornado, but it rather relies on distributed parallelism and adaptive mesh refinement through AMRX. So they have, in standalone Thornado, they have coupled AMRX in, or Flash-X, where you basically that block or in the octree, every time a new block is created, we basically fill that information in Thornado, and then we do the evolution on single blocks. All right. Let me see what the time is, because I realize that it's late and we might skip through these slides. All right. So let me briefly introduce how we do the phase space evolution equations and how we do the discontinuous Galerkin discretization of the phase space. So basically, you have in DG, you evolve degrees of freedom within an element, and the elements only talk to each other via fluxes through the phases. So there's no reconstruction needed, or in principle, there's no data needed from outside of your own element. And the way that works in Thornado is that we do the discretization for in both space, and the spectral is in DG. So we have the same number of elements of polynomial degrees of freedom in the spatial and the energy dimensions. And usually when we do, for reasons that will become apparent later when I talk about the interfacing the DG grid with the finite volume grid, we usually use linear elements. So we have 2 nodal points per element in the spatial and then also in the energy dimensions. So we evolve the system. We basically, the so-called semi-discrete DG problem, you have to integrate your evolution equations against test functions in that polynomial space, and then basically do the evolution and supply numerical fluxes that approximate the real fluxes through the boundaries for each of the elements. And on each element, we use Gauss-Legendre collocation points, and our basis functions are Lagrange polynomials. As a further detail, we used what is called the nodal collocation discontinuous Galerkin method, which means that we use the nodal points also for quadratures to approximate integrals. And then the WQs are the weights associated with the nodal points that I've just talked about, which means that when you do integrals over elements, you can basically just approximate them as sums, and then use the weights to do the integrals over your sums. And in general, when you do that with if you have a function that is where the polynomial order of your functions is 1 less than the number of points, the integrals that you do over the elements are exact. And that is going to be important when we do reconstruction and restriction and prolongation. As we've heard before in the talks of today and earlier, we discretize the system in space using the DG method, and then you basically have a time evolution where you have a system of ODEs that you need to solve, similar to the method of lines, but at the moment we use Lie-Trotter splitting for the different physics. And you basically end up with a system that has non-stiff terms in the free streaming regime and stiff terms in the collision for the collision operators. And that it lends itself to use an implicit, explicit, or IMAX time stepping routine, where the time stepping is typically set by the explicit part through a CFL condition. And some of the challenges that we encounter when we do this are the accuracy in the diffusion limit or the optically thick limit, and we want strong stability preserving properties. And of course, the implicit solves are expensive because you need to solve nonlinear systems. For the neutrino-matter solver, there's a nested algorithm where we have an implicit update on the primitive moments. So D and I are the Lagrangian number and number density number flux. And they depend both on sources that come from the neutrinos, from the space-time, and from U, which is the solution vector for the matter. And we basically have two loops, the outer and inner iteration, where in the outer iteration we solve the matter and the neutrino updates. And then inside the outer iteration, we have an inner iteration where we update the neutrino quantities. And both are done as fixed point maps. And there's no need for a Jacobian or the solution of dense linear systems because we use a technique that's called Anderson acceleration that is being applied separately to the outer and the inner loops. And this algorithm has the advantage that we only need to do an opacity interpolation in the outer loop, so you don't need to reinterpolate all the opacities for the number of inner iterations that you need to do. And it's straightforward to extend for additional opacities or different species. You basically need to do the same thing for all 6 species and update the opacities. And as I said before, it's an order V over C model currently, which means that the density is unchanged, and this is going to change later when we do GR. So once you do GR, the density also changes due to the evolution of the neutrinos. And then finally, in order to put it all together, we have to couple Thornado with Spark. So we have to couple the finite volume with the DG representation. So that's similar to what Peter was talking about earlier, where you have your SPH, your particles live in a different world essentially, and they need to communicate back and forth with where the space-time lives. And what we do there basically is that we have elements in Thornado that are larger than the finite volume cells in Flash. And as I've said before, we use linear elements. So we have 2 nodal points per dimension in Thornado. And that means there's a one-to-one correspondence between the Thornado nodal points and the cell centers of those finite volume cells that they're covering basically. And in order to go back and forth between, so the fluid needs to be updated in Spark, then it needs to be brought into the discontinuous Galerkin framework of tornadoes, so it can be updated through the nonlinear evolution with the neutrinos, and then it needs to be brought back after it has been updated into the finite volume solver. And what we basically do is we reconstruct the DG representation from the finite volume cells by basically requiring that the integrals over the cells are equal in both cases. And then you do the inverse of that reconstruction matrix to basically do the projection back onto the finite volume grid. And there's no loss of accuracy going back and forth between the different representations. And most importantly, there's no loss of conservation because the integrals are always the same. And in order to show that this is working, I'm showing here results from a so-called deleptonization wave problem where we take a profile from a different supernova simulation and keep the fluid fixed and then evolve it in both standalone Thornado and Flash-X. And in Flash-X, we also keep the fluid fixed, and that basically means that we have to still project and reconstruct the data back and forth for each time step. And the name discontinuous Galerkin comes from the fact if you squint your eyes here and see how the nodal points actually behave, you see that they are kind of counterintuitively tilted. But if you integrate over those to get the element average, you see that it follows what Flash is expecting. So that's an important test to show that this algorithm of going back and forth between the finite volume and DG grids is actually working. Then finally, the last ingredient is WeakLib, which is our tabulated EOS and neutrino opacities library. So the neutrino opacities generally depend non-linearly on rho T and YE, as well as on the energy of neutrinos. And when I started working at the lab almost 6 years ago, I was tasked with the process of the WeakLib that I was given. It's called original WeakLib in this table, and I was tasked with updating WeakLib to get physics parity with Chimera code, which is another supernova code that we have at the ORNL University of Knoxville collaboration. So basically, in particular, I've added nuclear Bremsstrahlung and electron-neutrino, anti-electron-neutrino pair annihilation to heavy neutrinos. And the most difficult part so far has been the addition of the electron capture table that I'm going to talk about in 2 slides. So WeakLib provides the user with routines to do equation of state inversions. So you can go from internal energy to temperature, or pressure, or entropy to temperature, and interpolations of the opacity kernels in rho t ye and neutrino energies. WeakLib, similar to Thornado, is fully accelerated using OpenACC and OpenMP offloading. And the way we do this is using macros. So we basically have, before each loop, we have macros to do just usual OpenMP offloading and OpenACC offloading. And the code has been optimized to run very efficiently on the GPUs, and we get nice speed ups when we use our tables on the GPU. Then finally, so I was talking about how the electron capture table was difficult to do. So during the initial gravitational collapse, what sets the subsequent evolution is the deleptonization of the core. So you start out with an electron fraction that is quite high, and as you collapse, the neutrinos start become captured by heavy nuclei, and that drives how deep the trough is in the YE profile during collapse. And in order to capture that process correctly, we updated our tables to include a much more accurate treatment of this process, which uses NSE folded electron capture table. And that was first done in 2003 and is still kind of the standard for this process, which is compared to the previous treatment from Fuller et al. In 82 and Steve Brin's canonical opacity set of 85. And what we basically had to do there, the way this table is constructed, it's because it's not active in the full range of the EOS, so it's kind of skewed along rho, the temperature, and the electron fraction, and in this way they can get away with having a really high, it's equidistant bins. So the blue ones is the electron capture table, and it basically has a very accurate spectrum that you need to capture in order to capture this process correctly. And I basically put the full table into our WeakLib opacity tables, and then you had to write code in order to get this process treated correctly in WeakLib and Thornado, because what our energy bins usually look like are those green ones. And what you have to do is you have to interpolate the electron capture table onto the nodal points that I'm showing here in red, and then you have to integrate over the bins in the discontinuous Galerkin formulation and renormalize the spectrum so that the total emission of neutrinos that you get from electron capture table is still the same as in the original one. Otherwise, you'd be emitting not enough or too many neutrinos. And that caused some gray hair, but it's finally working now. And then finally, as I said, we have nuclear burning. So in the high density regions where we use the SFHO EOS, we basically determine the composition by just evolving the electron fraction of the matter together with the neutrino radiation transport. But in lower density regions, this becomes less and less accurate. And actually, if you want to put lots of the star on the computational grid, it doesn't work at all anymore, because the cutoff, lower density cutoff for the SFHO table might be higher than the actual densities that you reach inside your domain. And there we basically use the Helmholtz EOS and use the XNet code to directly evolve the mass fractions of all included species. And then our hybrid treatment basically linear interpolates between the two regimes in a transition region and density. And I'm showing here two evolutions where we show the electron fraction and the entropy as a function of density, and the red shaded region is our transition region where we go between the two. And you can see that with the hybrid equation of state, we can go to lower densities and basically put more of the star onto the grid. All right, quickly, a couple of results. So here's the collapse and post-bounce evolution of a 12 solar mass star with that marriage of the 3 different codes that I have introduced. So for this run, I've used Flash-X with the paramesh AMR backend. We do 1D spherical coordinates with the spatial domain going from 0 to 32,000 kilometers, which is only possible due to the hybrid EOS, because SFHO wouldn't go to that low densities. We have 8 AMR levels with a base resolution of 128 kilometers and a maximum resolution of 1 kilometers. And we basically do fully adaptive mesh refinement with criteria based on the density, pressure, velocity, and the shock variable. We have self-gravity with a GI effective potential. Hydrodynamics, we do Spark with the Wiener Z reconstruction. HLLC Riemann solver and RK2. And in Thornado, we use 16 energy elements with 2 nodal points. We evolve all 6 species in 4 moments and using the updated opacity set from WeakLib. So just to note there, if you think about GMHD, there's like 8 to 10 fields, right, per cell. And here with the spectral transport, we have 16 times 2 times 6 times 4. So we have 7 plus, if we have ghost zones, we have 700 of the order 780 degrees of freedom that we evolve. So basically you have a 100-fold increase of work per spatial grid point. And we can do that efficiently because the entire transport is offloaded to the GPU, and we kind of treat it as being for free because the GPU can do the 100-fold increase in work at the same time as the CPU evolves the hydrodynamics. This was done with SFHO, and we have the nuclear burning we do with XNet with the ANP 56 network, which is 56 isotopes. And the hybrid transition region is between 1 to the 7 and 5 times 10 to the 6 grams per cubic centimeter. So here's some evolution. So time coded is time from onset of collapse through bounce and the post bounce evolution. So you can see how the YE is quite high, so it reaches 0.43 or something initially. And then you can see a couple of things. So as we doing collapse, we allow for more and more refinement as the central density increases. So you can see how the solution kind of comes closer and closer to the origin as we add more and more levels during collapse. And then basically the YE at some point stays relatively constant because once the protoneutron star has formed, it's in thermal equilibrium, and the subsequent evolution of the really deep core is on the second time scale. So that should remain nice and flat. And the trough there that I was talking about, that is basically the deleptonization that you only get correctly when you use the correct rates for electron capture table. We have the radial resolution there, also color coded, the electron neutrino root mean square energy, and the velocity in units of C, which I always get flack about because in the supernova community, they use CGS units, and they always laugh at me when I plot things in C, but I have to maintain some sort of integrity. Finally, there's some plots showing the lepton number conservation. So we see that the total lepton number is conserved quite well. And we basically monitor the lepton number of the fluid. So you see that the fluid becomes deleptonized, so it loses lepton number at the same time as the neutrinos start rising, and then the neutrinos basically start flowing off the grid. So once the neutrinos are in the free streaming regime, there's nothing that holds them back anymore, and they're just allowed to leave. And finally, we also show that the total change in mass is conserved to round off, and that it's basically the change in mass is what is flowing outside of the domain. Then here's some recent results of a code comparison that I'm doing for the code paper that we're writing, where I've left out the other code because I just want to focus on Tornado. So there's 3 different profiles of the density, electron fraction, and temperature for a similar collapsed metal at 100 milliseconds post bounce. So you can see the shock location in the density and the temperature, and again this trough in YE, and then it goes to a half outside. And then some neutrino quantities. So here we're plotting the root mean square energy, which is defined as the integral. So it's a gray quantity because it's energy integrated. So it's the number density times e to the power 5, the integral divided by the 3rd power of the energy, and then taking the square root. And then we have the luminosity as a function of radius. And there's a small but barely noticeable difference between the muon and the anti-muon neutrinos, and that is due to the fact that our neutrino electron scattering is inelastic. So there's small changes in those species, and those become more pronounced if you actually go to the updated opacity set, where once you have weak magnetism corrections, that splitting becomes larger. Yeah.
I'm wondering about the temperature. Why is there the peak like not in center slightly off? Is that something typical?
You mean that one here?
Yeah.
That is where the sorry. The question was why there's a peak at the temperature, not at the origin, but slightly further out. So deep inside, so that peak here, I think, is numerical. So that should be flat, and then it becomes hotter there because that's where you start becoming not being in thermal equilibrium at some of the energies of the neutrinos. So there's some heating going on there, and then it kind of drops. But that's not numerical. The one at the origin is. So we're still looking into that. All right, and then finally, before we're all done, we do the same thing, but this time in 2 dimensions in cylindrical coordinates. So again, fully adaptive mesh refinement. The domain that goes from 0 to 16,000 kilometers, and in the Z direction, it goes from minus 16,000 to 16,000. Essentially the same setting as before for the 1D results. And then we have, so we showed 2 movies. We have the one on the side started first. So you saw the evolution of putting temperature on the left, electron fraction on the right. So the star was collapsing. You formed the bounce shock. You saw the shock wave was traveling out. Then it stalled. Then it becomes, there's some convection going on in there. And it's basically that balance between the heating that comes from the neutrinos that are emitted from the proton-neutron star inside the gain region and the ramp pressure of the still infalling material. And you can see that it's still infalling because the temperature here changed. So in the beginning, this was more yellow, so it was material that was closer in, and the later stages, the material that falls in is basically at a YE of 0.5. And here's the same thing. We're going to show the grid. So the resolution is color marked, just to show that the grid is dynamically adapting to the evolution. None of these models have exploded yet, and unfortunately, and I had to stop running them. But this is kind of so we've compared this with other results using Flash-X as well, and especially in multi-D, there seems to be some discrepancies between the different codes of how easy or how hard they explode, and our setup, I guess, was challenging. But I have to add that in the outlook I'm going to talk about is there's one key process that is still missing, which is non-isoenergetic scattering on nucleons, which helps with the explosion. But we're working on that. And finally, for the 2D results, so I said they didn't explode. So you saw here's a couple of different resolutions and a couple of different things that I tried. But basically, the story is always similar. So initially, the shock expands rapidly until it gets to a maximum expansion, and then it's basically being pushed back in because the heating from below is not enough to push it out against the ram pressure of the infalling material. And we've evolved this for like 600-700 milliseconds post bounce, and there was no signs of explosions yet. So we'll have to revisit those when we get more accurate weak physics in. Finally, in terms of performance, in order to finish the Exastar or the ECP project, we had to run the so-called challenge problem, which was a full 3D full physics run that we ran on 50% on Frontier. And there we basically evolved, we collapsed in one dimension and then mapped the spherically symmetric one-dimensional collapse profiles to 3D. And then it's quite faint, but you can see how the code then self-consistently refined to get the final refinement. We only got a speed of about a factor of 4, but there's lots of parts that are expensive. So in that 3D run, the nuclear reaction network is actually quite expensive, and we didn't run the nuclear reaction network on the GPU yet. But the transport basically becomes for free because we run it on the GPUs. All right. So as current and future work, we're currently implementing muons both in Thornado and WeakLib, and then there will be storage considerations becoming important for the opacity tables because the dimensionality will increase for some of them. So if you think about emission and absorption, for instance, on nucleons, which, as Jonas said earlier as well, is a function of the neutrino energy, rho t, and the proton fraction, this is going to be now a 5-dimensional table in terms of the neutrino energy, rho, temperature, ye, and y mu. And this effort is being led by Luca Boccioli, who's a postdoc at Berkeley, and Margot Fitz-Axon, who's a postdoc at ORNL. We're also in the process of implementing the last opacity for physics parity with Chimera, which is non-isoenergetic neutrino nucleon scattering, which is led by Christian at ORNL. And this is thought to be very important for the shock revival stage because the isoenergetic scattering, by definition, cannot heat the fluid when the neutrinos scatter off the fluid. And then finally, we're also in the works of working on a dynamical space-time and GMHD solver in Flash-X with actual method of lines instead of Lie-Trotter splitting, which is led by Steve Fromm, who's a postdoc at ORNL. And then we, as Helvi was saying earlier, we have a project with the summer student Cheng from UIUC to supply Flash-X with non-trivial GMHD initial data. And at first I said that Cheng is working on that, but then I remembered that I'm not allowed to say that he's working, so I had to rephrase this. All right, and then finally, in the last minute or so, let me dispel with some myths that I've heard as recently as this week, that the OLCF resources are only accessible to if you have DOE funding, which is manifestly not true. So you can, through the main 2 flagship programs, which is INCITE and ALCC, you can actually compute on our machines if you don't have DOE funding yourself. So, and INCITE in particular is the most attractive one because it's really open science. So a large fraction of the machine, the total node hours per year are allocated for open science. ALCC is more programmatic in the sense that the science that you propose has to be aligned with core capabilities of the DOE. So if you want to do binary black holes, you probably wouldn't be able to do ALCC, but if you do R-process nucleosynthesis and binary neutron star mergers, then you might go in through the nuclear physics part. It's a bit of unfortunate timing because the INCITE deadline for this year is on Monday. So the fact that I tell you now might not be enough to write a fully fledged proposal, but it's still good to know about these things and to be prepared for future years. And the most interesting for new users is the so-called Director's Discretionary Program. So those are in general small allocations at the OLCF, which are basically reserved for porting and benchmarking your codes on our systems, and also to do preparatory work to submit INCITE or ALCC proposals. And those are usually the best pathway for new users without existing allocations. So let's say, Peter, you want to do your co-array Fortran on AMD hardware. That would be a way to get your foot in the door, to get on the machine. They're modest amounts, so the allocation is usually around 5,000 to 20,000 node hours, which on the frontier nodes is still significant chunks of compute time compared to CPU systems. But it's basically a pathway to kind of get your foot in the door, get your feet wet, and be actually able to port your codes on the machine. And I think there might be some people on the Zoom call that can attest to that they have used those DD allocations successfully in order to prepare scaling plots and benchmarking and porting their codes. But the most important thing is that no, you don't need to be DOE funded to run on our machines. There's a relatively low hurdle entry type level allocation, and then the large ones, they are more involved. So the DD allocations are basically, they're reviewed internally by staff members like I and my colleagues. And the INCITE allocations as a two-way process, two-stage process. They're reviewed by staff members of the OLCF and the ALCF, the Argonne Leadership Computing Facility, for their computational readiness, so that we make a judgment call on how ready the code will be to run. So if you propose to run your single-threaded code that runs on your mobile phone on and you want 1 million node hours on Frontier, we're probably going to say that's better. That better be Nobel Prize worthy science that you want to do with it. And then after the computational readiness that is done internally, then they go to an external science panel, and then they get ranked, and then it's but that is external. But yeah, any questions you have, if you're interested in those, just always write me an email or catch me on Slack or whatever, and then I'll be happy to help and enlarge the user base of the OLCF. With that, here's a list of my collaborators, my funding, and thanks for your attention.
Question from the audience, Vassilios? Yeah, quick question and quick comment. First, I want to say about the INCITE and the DD program there at Oak Ridge. It's a very similar process out at NERSC for Perlmutter, because again, if you're funded under DOE Energy Science Research, then they have a similar process for Perlmutter, and definitely the DD and the INCITE. But then also we have faculty who have already gone through the INCITE process and are involved with it. And this is a fantastic program also, get time on Frontier. So I just wanted to say, we already have people doing plasma physics, and in particular, Phil Morrison here in our physics department is already involved in a lot of this. And both systems, Oak Ridge is fantastic, what you guys got, but the Perlmutter system at NERSC was the prototype for Frontier, the first exascale system, and then your Frontier system was the final big one. So Perlmutter is also a fantastic system if people want to do simulation work.
Yes.
Scale up to Frontier. But then the second question I wanted to ask was on your Exastar, and in particular on your Flash-X, I'm very happy to see, people doing work with Flash-X. We've already been developing framework plasma physics code in Phil's group using Flash-X for a couple of years now. But the thing I'm curious is you mentioned your Exastar code using Flash-X with the Paramesh AMR code.
Yes.
Paramesh was actually put into Flash-X as a backward compatibility to the older Flash code, and they needed it so people are running older Flash codes. They can jump to Flash-X and keep that going. But Flash-X was actually developed with the primary purpose of putting AMR-EX in as the AMR code.
Yes.
So I was curious as to why you stayed with Paramesh AMR code, or is that like you were literally, when you're developing your Exastar code, you were actually starting in the old Flash code and then you upgraded, but you wanted to keep backward compatibility? Is that the reason that you kept using Paramesh instead of AMR-EX?
All right.
Repeat the question.
All right. Yes. So the question is why we use Paramesh instead of AMR-X.
Yeah, that's maybe.
It is a loaded question, and
It's a difficult question.
it might be above my pay scale. But in general, what we've seen is that the scaling with Paramesh is much better still than.
Well, that's interesting.
Yes. So
The main great Flash-X was to upgrade Flash to use
Yes.
AMR-EX. If you're saying that upgrade actually doesn't work that well.
those are your words, not mine. The
Flash-X was started.
Yes, yes.
upgrading AMR.
Yes, the Paramesh has worked very well for us in our case, and
Okay.
that's
So I would like to
good.
follow up with you what your experience has been. I don't want to waste more time. I would love to follow up.
The question online, and I would like to take that if you can, and then you guys can continue.
Yeah, we can.
Because the online people might have.
Can't hear it.
Can't hear it, and you guys are here, so.
Yeah, I just want to say, I want to follow up with him on this issue about what they learned about this.
Yeah, but you guys can probably do that
Offline, yes, of course.
So Roland has a question. Roland, please speak up.
Thank you. So I guess I have a sciencey question. In your presentation, you say that you get the neutrino transport for free because the GPU does in the same time that the host does the fluid evolution. In this case, does this mean that you have to ship large amounts of data from host to GPU for every single time step?
Yes, because we do the whole the grid going back and forth between the finite volume grid and the DG grid.
And that doesn't limit you.
No, it's still faster to do it this way because we're in the process of porting all the components onto the GPU, and then we'll get around that. But it's still it wouldn't be possible otherwise. It's the cost of the transport otherwise would just be prohibitive. And the GPU has actually we can put enough work on the GPU to make that work. So we can hide some of the latency, and then we do some asynchronous Go self-filling, and then the Poisson solve is actually asynchronous as well because it can start while some of the other physics is still running. So there's some ways to hide that overhead of moving the data back and forth. But we usually run with couple of ranks per GPU. So it's not that model where we just have one rank that has access to one GCD. So on Frontier we have 4 MI 250X, and each of those have 2 GCDs that are logically seen as a GPU each. And we can I usually run with 7 ranks per GCD. So we use more than one, the number of blocks per rank than on the GPU. And that works well. So you can hide some of the latencies that way. Which is of course going to be problematic once we do the tables in higher dimensions, because they're going to be, if you don't do something clever about it, the tables are going to be so large that they're going to bump on the GPU memory limits, and that's something we're thinking about what we're going to do there.
Thank you. Can I follow up, or am I keeping people from lunch or blocking other questioners?
We're way past lunch, so you can.
Well, dinner.
I would suggest that any discussions for further discussions offline or by other means. And I said, let me thank Vassilios again for his talk. And this concludes the session of today, I believe. Johnny, you should probably take over now, I guess. I have to know how this works.
Yeah, so I think that was the talk today, and we will see tomorrow at 9 a.m.
Take care, bro.
Yeah.